y and everything else. So what's going to happen to this constant by itself? It's going to kill it. Kill it, killer. What about this? What's the derivative of x by itself? 1. Minus 4y goes along for the ride. What's the derivative of x squared? 2x times 10y becomes 20xy. Nick, do you see that? Okay, so now, Nick, I'm going to pick on you for this one. So if y is our variable this time, what's going to happen to this term when we take the derivative with respect to y? That's 2. Is there a y in it?
No.
So it's going to go away. Great. Is there a y in this one?
Yes.
Good. What's the derivative of y? 1 times negative 4x becomes negative 4x. Okay? What's the derivative of y here? 1 times positive 10x squared. Do they make sense now? Did you overthink it? That's okay though. Once you get it, it's going to be in your head forever. Well, maybe not forever, but at least till the end of the semester, which is all you need, right?
Like
Let's be honest. Yeah, 3 weeks even. What the hell? Why not? Okay. Does it make sense though? Okay. Awesome. So let's take a look at number 21. 21, Sally, you wanted 21? Okay. Was this the slope of the tangent in the positive y direction to the surface z equals 3x plus 2y minus 7e to the xy at some point? Okay. So we're finding the slope of the tangent in the positive y direction. In positive y direction. Now they wrote out positive y direction, but I'm going to shorten that and say positive y hat, which is the same as saying positive y direction to the surface. Z equals 3x plus 2y minus 7e to the xy. And we're doing this at 3, 0, negative 2, positive 2. I didn't forget. Dang, I keep tearing this poor page. It's not going to make it. Oh well.
It's a good thing they're free for me. Sorry, Buck.
Okay, so first of all, what is it asking us to find? Slope of the tangent, and is another way of saying derivative, right? So it wants us to find the derivative in the positive y direction. So now we're doing the partial of z with respect to y. Okay? All right. And just like in the before I start doing the math here, let's explain this in 2D. When we had a function in 2D, we plugged in, this is a point in space, some x and some y. We plug in an x and we get out a slope, right? The y doesn't enter into it, does it? No. So the input variable goes in and we get a slope out. What are our input variables here? X and y. So do you think z enters into this? No. We're going to plug an x and a y in and we're going to get out a slope in the positive y direction. So what we're going to do here is we're going to take a partial with respect to y. We're going to plug in x and y. X is going to be constant. Y is going to vary from 0 to 1. And we're going to see how that affects z. We're going to look for a slope and see how z goes up or down if we vary y. So here we go. What's the partial of z with respect to y? Is there a y on this term?
No.
No, so you kill it, killer. Is there a y on this term?
Yes.
Yes, what's its derivative? 2. Good. Okay, is there a y in this term?
Yes.
Yes, so the derivative of e to the anything is the derivative of the anything times the original function. What's the derivative of xy with respect to y? X. So we're gonna get minus 7x e to the xy. Does everybody see that? Everybody cool with that?
Mm-hmm.
Any questions so far?
So e to the x of y is just e to the x of y, right? And
Not quite. The derivative of e to the xy is x e to the xy when we're doing it with respect to x, or sorry, with respect to y.
oh, so you're doing the u and the u prime.
Yeah, so think of this
Oh, the
as,
u prime and u.
think of this as e to the u,
Mm-hmm.
and we're taking the derivative of u with respect to y. So what's the derivative?
I thought I was gonna be here on time.
It's okay. No worries, Audrey.
Those tallies are really getting to me.
But at least
I'm like,
it's
I need
fun,
to beat the tally today. Damn it.
right? But at least it's a fun way to do it, right?
I guess. Do I get extra credit for being late and getting on the board?
No. Do I get extra credit for being late? No.
If that was the case, I'd have like straight
I'd be
A's right
so
now.
late. I'd be so late. No, seriously. So if you're taking the partial of z with respect to y, then the derivative of xy is just going to be x, right?
Mhm,
The derivative
yes.
of y is 1, x goes along for the ride. So this is what pops down, Maria. Does
Correct.
that make sense?
Yes.
So that's what we're doing here. And now you just plug in your 3 and your 0. So the partial of z with respect to y at 3, 0, 2 is 2 minus 7 times 3 e to the 3 times 0, which is like saying 2 minus 21, which is negative 19. God, you guys can do this in your head. No calculator necessary. Seriously. So I could interpret this in my head too. So if I, at this point on this surface, if I hold x constant at 3 and I vary y from 0 to 1, z is going to decrease by approximately 19. Zoom time. And that's it. Any questions? Saeed? Are you sure?
Bless you.
Excuse me.
Bless you.
And that's it. Okay. Let's do the next one. What, sweetie?
Something like this could be on the test.
Yes. Yes. Yes, it is. Is it gonna be on my test? Yes. Is it gonna be on the final? Yes. 53.
It's all easy as long as it doesn't have.
As long as it doesn't have E. E is what trips you up. Practice. And call me. That's what I'm here for. 53. Production. Was this the Q equals 75K to the 1/3, L to the 2/3? Yeah. Okay. Q equals 75K to the 1/3, L to the 2/3, where K is capital expenditures in thousands of dollars. I almost wrote that with the K. K is capital expenditures. In thousands of dollars. Okay, and L is the number of labor hours. Okay, so this is output Q. produced, or whatever you wanna look at, okay? Find the partial of Q with respect to K. I'll leave partial of Q with respect to L up to you guys. When capital expenditures are 729,000 and labor hours are total 5832, and interpret each answer. So find partial of Q with respect to K when K is 729 and L is 5832. Find partial of Q with respect to K when K equals 729 and L equals 5832, and interpret. That's not so bad, is it? No. Okay, well, what's the hardest part here? Aside from looking at it and going, ew. In the book, this said K equals 729,000. But it's not, is it? Because K is capital expenditures in thousands of dollars. So we're gonna have to do a little conversion. We're not putting 729,000 in for K, we're putting 729 in for K. So far, so groovy? That's the first thing. Because K is in thousands of dollars. So we need to change the number we plug in. And the second thing is, what's my variable? K. So what's constant? L. So I'm holding labor constant at 5,832 hours. What am I varying capital expenditures by? No. What am I varying capital expenditures by? $1,000. Because if K goes up by 1, it's actually going up by 1,000, isn't it? Right? So we've got to know that. That's the first thing. That's the first tricky thing. It's not a trick, but it is tricky. So when we do the partial of Q with respect to K, what's constant? L and 75. So what's the derivative of K to the 1/3?
1/3 K.
Okay, so I could write it out like that, right? I can leave the 75 and the L with the 2/3 the same. And I can just take the derivative of K right in the center of that. So like Saeed said, I can make this 25K to the negative 2/3, L to the 2/3. So far, so groovy, guys?
How did he get the 25?
The 25? What's 75 divided by 3?
Oh,
It's just 75 times 1 divided by 3. So 25 right here. Now we plug and chug. So we're gonna do 25K to the, whoops, K has a value. It's 729. To the negative 2/3, L is 5832. To the 2/3. And what does that give us, guys? 100. So the partial of Q with respect to K at K equals 729 and L equals 5832 equals 100. So what does that mean?
That would go from 729,000 to 730,000.
In capital expenditures,
Capital expenditures.
and you're holding your labor constant at 5,832 hours. That matters.
Fixed costs are constant.
Your output increases by how much? Yeah, so that extra $1,000 at that level, with that precise level, gives you an extra 100 units of output. Give or take. Does that make sense? Questions?
so you got minus 2/3 for K, right? Why didn't L why L did not change? Because it still has
It's
the,
constant.
oh,
It's a constant. K is our variable here. So if we're taking the partial with respect to K, everything else is constant.
okay,
So L to the 2/3 just goes along for the ride,
okay.
right? Okay. Any other questions on this one? You guys ready to tackle something fun? Doo-doo-doo. Doo-doo-doo-doo.
I knew you were gonna do that.
Shut up. Doo-doo. Oh, that's so fun. Today we're gonna talk about Cola Wars.
How was it?
Raise your hand if you were not alive in the 80s. God, I'm old. All right. Really? None of you, like, really?
89 doesn't even count.
Yeah, not really. Yeah. Okay, so I want to talk to you guys about multiple variable applications. That's our lecture today, but I'm going to sort of mix it and match it and weave it in and out with other topics. Sort of tie it all together. You guys have sort of learned this semester that this math doesn't exist in a bubble. There are lots of applications for the type of math we've been doing in this class. You can apply it to a lot of different things. It's really useful in our daily lives, not on our level, but the things that affect us use this math all the time. So for example, raise your hand if you carry an Android phone with you. Okay, raise your hand if you're an iPhone. All right, find it out. Which is better? Go. You might as well turn that off now.
Android.
You might as well turn that off now because this is a round robin conversation.